So, we looked at boiling in the last lecture. Today we are going to move to condensation. So, what we are going to see in today's lecture is we are going to look at how to characterize condensation process, and once again the objective is the same, to find out the heat transport coefficient. What is H and what is average heat transport coefficient? So, that is what we are going to see. Okay. So, what happens during condensation? We looked at boiling, where heat is supplied to the fluid and the fluid is converted from the liquid to the vapor phase. So, there is a phase change that is occurring because of heat transport from the wall or a solid to the fluid. What happens in condensation is exactly the opposite process, where the fluid is going from vapor to the liquid phase, and while doing that it is also liberating heat which is taken up by the surface or a wall which is present next to it. Okay. So, it is the reverse process where the latent heat is liberated. So, during condensation it is the latent heat which is released by the fluid, and in boiling it is exactly the reverse. It is the heat that is taken up by the fluid in order to go from a lower energy to a higher energy state. Alright. So, now, so there are 4 types of, so once again obviously the latent heat plays a role here. So, HFG, which is the latent heat of the fluid, plays an important role. So, there are 4 types of condensation. Okay. So, one is the dropwise condensation, and then have dropwise suspended condensation, and then the third one is you have film condensation, and the fourth process is direct condensation. So, these are the 4 types of condensation process. So, the first one, dropwise condensation, what happens is that in a dropwise condensation process, so supposing if there is a wall which is located, okay, and there is, let us say, vapor which is present, and let us assume that it is a quiescent vapor, which means that the vapors are not moving, just stationary, and let us say that the vapor is at some saturation temperature, which is the condensation point, and the temperature of the plate is Ts. So, Ts should be less or greater than Tsat. It should be less than Tsat, because vapor is now going to lose heat, it is going to form liquid, and that heat is being taken up by the wall. Okay. So, now what happens is you have drops which are formed along this surface. So, these are drops which get nucleated during the condensation process, and so when it gets nucleated, they slowly drop down one by one, and then the liquid is collected. So, they slide along the surface of the wall, and then the liquid is collected, or the condensate is collected. Okay. So, that is the dropwise condensation process. So, now if I look at the suspended, dropwise suspended condensation, process. So, suppose if I take a tube, if I take a tube So this is a fairly common dropwise, suspended dropwise condensation is fairly common in several heat transport equipments. So suppose if I take a tube, okay, and the surface of the tube is maintained at temperature Ts, and there is vapor which is flowing through this tube at, let's say, the saturation temperature Tsat. Okay. Now the bubbles will form along the curved surface of the tube, and then note that this is a horizontal tube, right? So they will detach and then they will drop into the vapor. They will all detach, and so now you will start having these drops which are suspended inside the vapor. So this is the dropwise suspended condensation process. And then the third one is where we have film condensation process. So suppose I have a wall which is at, let's say, temperature Ts, and there is vapor which is maintained, let's say, at Tsat, that's the saturation temperature. Now the condensation rate will be such that there will be a film which is formed here, a liquid film which is formed here, and the liquid film will start moving, okay, and then the condensate is collected at the bottom of that wall. Okay, so that's the third one, which is the film condensation process. So what we are going to see in today's lecture is going to characterize this film condensation process. Now the fourth one is the direct condensation, direct contact condensation process, and this mode of condensation occurs when you have contact between two different fluids at different temperatures. Okay. So now suppose I have a container. A simple way to visualize is, suppose I have a container and I have a fluid, let's say, and I have a tube here. I have a fluid which is maintained at Ts. Okay. Now I am going to pass gas through this tube, okay, and this is at Tsat. That's a vapor which is at Tsat. I am going to pass this gas through this tube. Basically, I am going to bubble the vapor through this liquid. Now what happens? This is at a temperature which is smaller than Tsat. That's smaller than Tsat, and therefore as the bubbles come inside, moment they come in contact with the liquid which is at a significantly or lower than the saturation temperature, then they are immediately going to form bubbles here, right? So that's called the direct contact condensation, where two liquids at different temperatures, one of them is going to condense because the other liquid is at a significantly lower temperature. Okay. So this is what is called as direct contact condensation. So what we are going to see for the rest of today's lecture is we are going to characterize the film condensation process. There is a difference. Here the dropwise, the drops are forming at a solid surface. Here the drops are actually forming in bulk. So the film is when you have significant drops that is formed, if the condensation rate is significantly higher, what you will have is actually the start with the bubble dropwise, and then it will actually transition to film. Because the condensation rate is significantly higher, before the drops fall, there will be more amount of liquid which will come and deposit on the surface, and so what you will have is a continuous flow stream of liquid, which is actually a film condensation process. Okay. So now I have a film here, and that's my boundary layer thickness, delta x, and I have vapor here which is at Tsat, and this is at a temperature Ts, and we assume that Ts is smaller than Tsat. Okay. So what's the driving force for condensation? It's the temperature gradient, right? So delta T the driving force is Tsat minus Ts. So that is the driving force for condensation. Now, so Ts is smaller than Tsat, so we can intuitively guess what is going to be the temperature profile. So that is going to be the temperature profile. So that will be T as a function of y. Okay. What will be the velocity profile? Same, different. So remember that vapor is at rest. It will be a okay. So you would expect that the u of y, we should have a maxima because vapor is at rest. Okay. So you are expected to have a maxima at the middle. So if you look at your textbook, there is a mistake in this particular profile that they have drawn. So you would expect that there is a maxima at somewhere in the boundary layer. So the vapor is at rest, it's at complete rest, and so you have u infinity is 0. Okay. So now I can write momentum balance. So all the usual things that you have been doing in this course. So the question is, why should there be a maxima, right? So remember that the velocity of the fluid at the wall, what's the velocity of the fluid at the wall? It's 0, because it's a no slip condition, and so it has to be 0. The fluid comes to rest, and the fluid is going to be at rest because the vapor is not moving. It's a quiescent fluid, so vapor is moving. So the fluid is now moving in the film. So it's bounded between two locations which has 0 velocity. So there has to be a maxima in between. Alright, so now we can write an x momentum balance. So u du by dx plus v du by dy, that's equal to minus 1 by mu, 1 by rho dp by dx plus x dot by rho. So note that I am using a plus sign because I have now my x direction is now in the positive gravity direction, plus mu by rho d square u by dy square. Okay. Now, so we make an assumption here. One could actually do without doing the assumption, but you will not get some insights that you will get. Okay. So the first assumption we make is that the u and v are very small, and that's not a bad assumption actually. So the velocity of the fluid inside the bound layer is very small, and therefore, okay, therefore the convective effect are negligible. Okay. So now, so if the convective effects are negligible, we can neglect the left hand side of this momentum balance. So therefore, we can write the momentum balance as square u by dy square, that's equal to dp by dx 1 by mu, that's mu of liquid, because the momentum balance is in the boundary layer, so we are looking at the liquid system, okay, minus rho liquid into gravity divided by liquid. Okay. So now we said that the vapor is at rest, right? So vapor is at rest, the velocity is 0, and also all the gradients are 0. All gradients are 0. So therefore, outside the bound layer, the momentum balance will be dp by dx, that's equal to rho vapor into gravity. So, this is the same thing what we did with the natural convection before. We just write the momentum boundary layer equations in the outside the boundary layer. Velocity is 0, all the gradients are 0, and therefore, the pressure gradient is going to be simply given by rho vapor. Remember, it is the density of vapor, not the liquid, density of vapor multiplied by gravity. So, now if I plug in that quantity, so you have d square u by dy square, that is equal to rho vapor minus rho liquid divided by mu liquid into gravity. So, that provides a mechanism to find the x component velocity profile inside the boundary layer. Okay. So, I can solve this equation uy, that is equal to g into rho L minus rho vapor divided by the viscosity of the liquid delta square delta minus half y by delta the whole square. Okay. So, that is the solution. Alright. So, now do we know the velocity profile from this expression? Yes or no? Yes? We do not know what delta is. We still do not know what is the velocity profile. So, really the exercise here is to find out what is the boundary layer thickness. So, we need to find out what is this delta. What is the boundary layer thickness at any location. So, until we find the boundary layer thickness, the problem is not complete. We cannot find the velocity profile, and in fact, the same issue will continue when you write a temperature balance. So, how do we find this? Okay. So, there are two ways of doing this. One is you could use y tending to 0. You could also use du by dy equal to 0. See, you are solving only inside the boundary layer. So, it is a fixed boundary value problem. You use similarity variable when you are having infinite boundary value problem. That is true. So, that is why, see, you have a definition for the boundary layer, right? Because the vapor is at 0, this will be the correct boundary condition that you have to use. And simply because we are interested in solving the profile inside the boundary layer. How do we find the boundary layer thickness? So, if we know the boundary layer thickness, we are done. So, now, so this is a sort of a simultaneous heat and mass transport problem. So, remember that when the condensation process occurs, there is a certain amount of condensate which is being collected, right. So, although we are not going to write mass transport equations, but what we are going to find is what is the total amount of condensate without doing this, we will not be able to solve this problem. And the reason is, so remember that when there is a condensation process which is occurring, there is a latent heat is being lost by the vapor to form the condensate. So, unless you know what is the total amount of condensate that is formed, you will not be able to relate the amount of latent heat that is actually being liberated by the vapor in order to form the condensate, because the latent heat is liberated per unit mass of the vapor that is actually forming the condensate. So, therefore, it is important to find out what is the amount of condensate that is formed, and that is how we are actually going to relate the boundary layer. And the reason why that works is the boundary layer thickness. So, remember that the boundary layer consists of the fluid which is the condensate which is formed. So, therefore, if you want to know what is the boundary layer thickness, you want to know what is the amount of fluid or liquid which is present in that location. So, that is what defines your boundary layer thickness. So, therefore, we directly get to the question of what is the amount of condensate that is being formed. Okay. So, now based on the velocity, okay, supposing if I call gamma x as the amount of condensate at any location, okay, so that is given by m dot by, So, suppose if I have the thickness of my plate is B on the other side, length of the plate. So, if m dot by B, I am using B because I want to be consistent with the legend that is used in your text. So, m dot by B is the amount of condensate that is actually formed, rate of condensate formation per unit length which is outside the bore. And so, that will be integral 0 to up to boundary layer thickness, the density of the liquid multiplied by the local velocity into dy. That is not difficult, we know how to do that. Okay. So, plug in this 0 to delta x rho L into G rho V divided by mu L into delta square y by delta minus 1 by 2 y by delta the whole square into dy. Okay. So, we can integrate this expression. So, that will turn out to be rho L into G rho V multiplied by delta x cube divided by 3 times mu L. Okay. So, all I have done is I have just integrated between 0 and delta.